So, welcome. During last lecture, we started with the concept of Airy stress function, and we discussed about Airy stress function that this particular Airy stress function is valid for the assumptions in which the fundamental assumptions which we made in the theory of elasticity that are applicable for Airy stress function. So the assumptions in theory of elasticity are same like that of which we learned about in solid mechanics or in analysis of mechanical element or strength of material. In that subject already we are familiar with the assumptions that material should be continuous, then material should be homogeneous, then material should be elastic, then displacement or the deformation should be small. So these are certain assumptions. Regarding this Airy stress function, the solution of elastic problems can be observed by exact method. Airy stress function is considered to be the exact method or the approach or inverse method. The stress function is analogous to potential function of the fluid flow or thermal energy flow. It is known as steady flow and can be represented as del square phi is equal to 0, where phi is considered to be potential function and del is considered to be Laplace operator. So, in Airy stress function, del square phi, this particular equation is equal to 0, is considered to be Airy stress function. Is it okay? Then, the Airy stress function has given the stress value. Suppose sigma xx is considered to be the stress along x-axis. Then sigma xx is considered to be del square phi upon dy2, and del sigma yy is considered to be del square phi upon dx2. Similarly, sigma xy is considered to be minus dou 2 phi upon dou x dou y. And suppose phi is any function, if we take the derivative of phi or partial differential equation of phi with respect to y two times, then that becomes the stress along x-axis. Similarly, if suppose del phi is any function, and if we are taking the differentiation of this function phi with respect to x two times, that is partial differential equation, then that becomes the stress along y-axis. And in order to identify the shear stress, we should have the equation sigma xy is equal to minus dou 2 phi by dou x dou y. So this is the Airy stress function. Is it okay? Before going to few examples, let us have the discussion upon one fundamental concept with Airy stress function, and this is the fundamental concept of the Airy stress function, that del square sigma x plus sigma y is equal to 0. So let us prove first of all the thing of assumption with which this Airy stress function is formed, and then we will go for the exact solution or some numerical problems of the Airy stress function. Is it okay? So from previous concepts, now we know that strain along x-axis. During last lecture, we have identified the value of stresses, value of strains, then value of the equilibrium equation, then compatibility equation of the strain, and while forming the compatibility equation of the strain, uh, we, uh, we go ahead with the assumption that sigma xx, that is sorry, epsilon xx, that is the strain along x-axis, is nothing but dou u by dou x. Okay, so that was that we have proved. This particular concept we have proved. Then strain along y-axis, that is epsilon yy is equal to dou v by dou y, that is the strain along y-axis. Then third thing is the strain, shear strain epsilon xy. So that we proved as dou v by dou x plus dou u by dou y. So strain along this shear strain. Is it okay? So this is considered to be shear strain epsilon xy. So these three things we proved initially, that epsilon shear, the strain along x-axis is dou u by dou x, strain along y-axis is dou v by dou y, and shear strain is dou v by dou x plus dou u by dou y. Is it? So that concept we have already proved. Now, as a first step of the derivation, in order to prove the del operator del square phi is equal to 0, because we already assumed in case of Airy stress function as del square phi is equal to 0, where phi is considered to be potential function and del is a Laplace operator. Then let us here take the support of these equations epsilon xx is equal to dou u by dou x. So if we differentiate this particular equation dou epsilon xx with respect to y and again two times, then this particular epsilon xx will get converted as dou 2 epsilon xx upon dou y2, because here what we have done, we have differentiated this epsilon xx two times with respect to y, and this is the partial differentiation equation. So left side terms we have differentiated two times, this becomes dou 2 epsilon xx upon dou y2, and then right side that is also differentiated with respect to y again two times. So this will become dou 3, because dou u already present. So after first differentiation, this will become dou 2u by dou x dou y dou x dou y, and in second differentiation it will become dou 3u dou x dou y2. Is it okay? So here we can understand from this equation 1. What is the equation 1? Equation 1 is the differentiation of epsilon xx is equal to dou u by dou x by two times, and we got the equation number 1 as dou 2 epsilon xx dou y2 is equal to dou 3u dou x dou y2. Is it okay? So this we can understand here as the equation 1. Then let us have this epsilon yy is equal to dou v by dou y. So this we have proved, and now this equation we are differentiating with respect to x two times. So after differentiating this epsilon yy two times, we will get dou epsilon yy dou x first, and then this will become dou 2v by dou y dou x first, and in second differentiation it will become dou 2 epsilon yy dou x2 is equal to, so this particular equation we have differentiated two times with respect to x, and then it becomes dou 2 epsilon yy upon dou x2 is equal to dou 3v. Is it okay? So understand here it is dou 3v dou y dou x2. Is it okay? So this particular dou v by dou y, which is differentiated two times with respect to x, in first differentiation it will become dou 2v by dou y dou x, and in second differentiation it will become dou 3v by dou y dou x2. Is it okay? So this is the equation which we can understand as the equation number 2. Then this third equation, that is epsilon xy is equal to dou v by dou x plus dou u by dou y. So this particular equation now we are going to differentiate with respect to x and with respect to y. So if we differentiate this epsilon xy with respect to x first, then it will become dou epsilon xy upon dou x, and when we differentiate same equation with respect to y, then it will become dou 2 epsilon xx dou x dou y. Is it okay? So this particular equation is differentiated with respect to x and with respect to y, and then this becomes dou 2 epsilon xy. So see here small correction we will have to make here. Epsilon xx, it is wrong, it is epsilon xy. We know that this is the epsilon xy term. So here you will make the correction, that is dou 2 epsilon xy dou x dou y. That means this particular equation is the first initially differentiated with respect to x, and later on that is differentiated with respect to y. When it is differentiated with respect to x, then it became dou 2v dou x2 plus dou 2u upon dou x dou y, and later on once again after differentiation with respect to y, it will become dou 3v dou x2 dou y, and here dou 3u. So it is already dou y, first differentiation dou x, and another dou y2 it will become. So dou x dou y 2. So after differentiation this will become this term, that is equation number 3. Here we can understand the equation number 3, that dou 2 epsilon x upon dou x dou y is equal to dou 3 v upon dou y dou x2 plus dou 3 u dou x dou y2. Is it okay? So now we are familiar with these three equations. What is equation 1, 2 and equation 3? Is it okay? Now let us have this particular dou 2 epsilon xy dou x dou y. So this particular term, equation number 3. Here, if we observe the equation number 1, then that equation number 1 is dou 3u by dou x dou y2. So here if you see, that is dou 3u by dou x dou y2. So from this equation number 1, what we will say, that this particular term which is present here, same term is present here also, so we can replace this term with respect to this term. So dou 3u dou x dou y2, this particular term we are replacing with reference to equation 1. Similarly, if we observe this particular term dou 3v dou y dou x2, then that particular term can be replaced by this equation number 2. So dou 2 epsilon yy upon dou x2. So that term we are going to replace. So with reference to equation 1 and 2, or substituting equation 1 and 2 in equation 3, we will get dou 2 epsilon xy upon dou x dou y is equal to dou 2 epsilon yy upon dou x2 plus dou 2 epsilon xx upon dou y2. Is it okay? So here we can understand that equation number 1 and 2 has been substituted in equation number 3, and we got equation number 4 as it is. Is it okay? As for Airy stress function, this del square sigma x and sigma y. So this concept we are going to introduce, or we are going to study as a Airy stress function. So we will have to convert all the language of this strain into in the form of stress. So this epsilon yy is the strain along y-axis. This epsilon xx is the strain along x-axis. This is shear strain. Then that shear strain we will have to convert into shear stress. Then this epsilon yy, that is strain along y, we will have to convert into stress along y direction, and this strain along x direction we will have to change as a stress along x-axis, and that's why the common equation which we already using number of times we have already used. So this equation we will use here also. Let us study this epsilon xx. As per our assumption, as per decided thing, this epsilon xx is the strain along x-axis. Then we know that whenever the condition is biaxial condition, because we know that uniaxial, biaxial and triaxial, these are the three conditions. In triaxial conditions, the forces are acting along three directions. In biaxial, we are considering the forces are acting in two directions, and in uniaxial, we are considering the forces acting in only one direction. Now, as far as concerned with this particular concept of this Airy stress function, only we are considering x and y. This particular equation is valid for x and y direction only. We are not considering, because already also we discussed about this, is that always deriving the equations are easy for in the situations when there is less thickness, because three-dimensional analysis is very complicated type of analysis. When forces are acting in three directions, then that becomes the complicated geometry, and that analysis is also complicated type of analysis. So always equations are derived for two-dimensional geometry, two-dimensional analogy, and then that are applicable for three-dimensional cases. Is it okay? So likewise, here also we have considered to be the biaxial conditions, that is x and y direction is present only, and that's why epsilon xx, we already know, we are already familiar with this biaxial condition, the stress strain relationship. We know that this equation will be equal to 1 upon e sigma x, because already this kind of equation we have studied whenever we have identified the relationship between different elastic constants. So E mu Gk are the elastic constants, and during deriving the relationship between E mu Gk, we have gone through this concept of biaxial stress, biaxial strain. And then the strain along x-axis is nothing but sigma xx upon capital E minus mu into sigma yy upon capital E. Under this assumption is that The forces are tensile in nature, and in x and y in both direction forces are acting in tensile directions. Means that's why in x direction this will be positive, but in y direction this negative term will present along x axis. So from that point of view, epsilon x, the strain along x axis will be considered to be 1 upon e into bracket sigma x minus mu into sigma y. Here we have considered this as equation number 5. Now similar concept is epsilon yy. This we can understand. So you will come to know that why this particular term has been written like this. Epsilon yy is the strain along y-axis, and definitely that will be also equal to sigma yy upon capital E minus mu into sigma xx upon capital E. Is it okay? So this will be represented by equation 6, and then the shear strain, the concept of shear strain, if we try to understand here, then we will come to know that epsilon xy is nothing but 1 upon capital E into bracket 2 into 1 plus mu into sigma xy, because this equation relationship between shear stress and shear strain. So shear stress upon shear strain is nothing but shear modulus. So here shear modulus, this concept, because G, we are writing G is equal to 2 into bracket 1 plus mu upon E. So here also if we transfer the shear stress upon shear strain in that form, suppose this is shear stress upon shear strain, then the stress upon strain, this part will be here, it will be considered to be G, that is shear modulus. And if this particular term is transferred on this direction, then that will become 2e into bracket 1 plus mu. So this is 1 upon. Is it okay? So that we can understand here. So now we have to take the cognizance of this stress strain relationship in, and we have to use that in equation number 4. So that's why let us try to bring in that form. So if we look to equation number 4, then this is the form that this is strain along y-axis is differentiated 2 times. Is it okay? So see here, that is strain along y-axis is differentiated 2 times with respect to x. Then here also we will need to differentiate this term epsilon yy 2 times with respect to x. And in equation 4, this epsilon xx is differentiated with respect to y 2 times. So dou 2 epsilon xx upon dou y2. So like this term, if we'll see here epsilon xx, then that we need to be differentiated with respect to y2 times. Then here it will become dou 2 epsilon xx upon dou y2. That is differentiation of this strain along with respect to y2 times. And then definitely this right side of the equation will also get changed as 1 upon e into bracket dou 2 sigma xx upon dou y2 minus mu into dou 2 sigma yy upon dou y2. So this particular equation is differentiated with respect to y2 times, and we got this equation number 8. Similar to that, suppose here if it is epsilon yy, then we will have to differentiate that epsilon yy 2 times with respect to x in order to get this first part of this right side of the equation number 4. Then this epsilon yy is again differentiated with respect to x in order to get this. We got dou 2 epsilon yy upon dou x2 is equal to 1 upon e into bracket. So this equation we have differentiated with respect to x. We got dou 2 sigma yy upon dou x2 minus mu into dou 2 sigma xx upon dou x2. So here you can understand this particular concept that this equation 6 is differentiated with respect to x 2 times in order to get the equation number 9. Is it okay? Then let us substitute this equation number 8, 9 and 10 in equation number 4, because suppose this equation 8, this is related with the dou 2 epsilon xx dou y2. So here this relation we can see here that dou 2 epsilon xx upon dou y2, and similarly here dou. So this equation we are substituting equation number 8 and equation number 9, that we are going to substitute in equation number 4. Is it okay? So let us put that equations here, and the substituting that equations here we got Because here in one more term is there, that's equation number 7 is also differentiated with respect to x and with respect to y. So initially it is differentiated with respect to x and later on it differentiated with respect to y, and that became equation number 10. And later on these all equations uh, so let us substitute this equation number 8, equation 9, equation 10, and if we substitute that 8, 9, and 10 equation in equation number 4, then we will come to know that this is 1 upon e into bracket 2 into bracket 1 plus mu dou to epsilon sigma xy dou x dou y. Similarly, all these terms which are present here after differentiating that are substituted here, and by cancelling the common terms, we got 2 into bracket 1 plus mu into bracket dou to sigma xy upon dou x dou y. So likewise, the common terms are calculated here 1 upon e, that common term which is present to the left side and right side, that is cancelled here. At the same time, whatever the multipliers of this mu that are also neglected, because we know that Poisson's ratio, this particular term is lateral strain to the longitudinal strain. Lateral strain is always very small, because already these two terms are very small. Lateral strain, that factor is very small, and again lateral strain to longitudinal strain, that is also very small. So Poisson's ratio is always near about 0.25, etc. So already these terms are higher order terms, and later on we are multiplying by 0.25. This value is definitely coming to be less. So that's why these mu terms which are multipliers of mu, so that are neglected. So by neglecting the multipliers of the Poisson's ratio, we got the equation that 2 dou 2 sigma xy upon dou x dou y is equal to dou 2 sigma yy upon dou x2 plus dou 2 sigma xx upon dou y2. So here you can refer this equation, which is the equation which is the outcome, that after substituting and after cancelling the common terms, whatever the values we are getting here, so that values are 2 dou 2 sigma xx dou 2 sigma xy upon dou x dou y is equal to dou 2 sigma yy upon dou x2 plus dou 2 sigma xx upon dou y2. So here this is the equation number 11 which we got here. Now some more thing we will have to take into consideration, because we are in the half of this derivation. We are here with dou to sigma x, so dou to sigma yy upon dou x2, and this is dou to sigma xx upon dou y2. Still something is needed here. For that purpose we are taking the reference of equilibrium equation. So if you remember, this is the equilibrium equation. What is that equilibrium equation? That equilibrium equation is a differentiation of stress with respect to x, that is dou sigma xx upon dou x plus dou sigma xy upon dou y plus capital X. So capital X is the body force, is equal to 0. Already we have derived this equilibrium equation at the first time. The first derivation which you studied in this theory of elasticity is the differential equation, and that is dou sigma xx upon dou x plus dou sigma xy upon dou y is plus capital X is equal to 0. Similarly, here if we see the dou sigma yx upon dou x plus dou sigma yy upon dou y plus capital Y is equal to 0. So that is also the different equation which we referred or derived as an equilibrium condition. Is it okay? So these two equations we have considered here. By taking the reference of this equation, equation number 12, and here equation 12 and 13 are present. If we differentiate this equation number 12, then here we will get that dou 2 sigma xx upon dou x2 plus dou 2 sigma xy upon dou x dou y plus dou capital X upon dou x is equal to 0. So what is this? This equation number 14. So this equation number 14, what this gives us? That is the differentiation of equation number 12 over here. So and that differentiation is with respect to x. So this particular equation is differentiated with respect to x. And we got dou 2 sigma xx upon dou x2 plus dou 2 sigma xy upon dou x dou y plus dou capital X upon dou x is equal to 0. So that is the equation number 14. Now, similarly, for this equation number 13 again, let us differentiate this equation with respect to y again. So equation number 13, we are differentiating with respect to y. And in order to be this equation, we get that dou 2 sigma yx upon dou x dou y plus dou 2 sigma y upon dou y2 plus dou capital Y upon dou small y. Is it okay? So that is the differentiation of this equation number 13 with respect to y, and we got the equation number 15 again here. Is it okay? So we can understand this term, that is how this equation dou 2 sigma yx dou x dou y plus dou 2 sigma y upon dou y2 plus dou sigma dou capital Y dou small y is equal to 0, how this term came. So we have taken the reference of this equation number 13. From 13, after differentiation of this equation number 13 with respect to y, we got this particular equation. Is it okay? So try to understand this thing. Then we should go ahead. Is it okay? So let us go ahead. Now this equation number 14, small rearrangement we are going to do here. So for that purpose, let us have that this particular term dou 2 sigma xy dou x dou y, that is present in equation number 14, which is written like this: dou 2 sigma x sigma xy dou x dou y, and these two terms, remaining two terms, are now transferred to the another side. Then this became minus dou 2 sigma xx dou x2 and minus capital dou x small dx. Is it okay? So like this, these two terms which are here, that two terms are transferred in order to have in the form of dou 2 sigma xx dou x dou y. So this is equation number 16. Similarly, so by taking the reference of this particular equation 15 again, that is dou 2 sigma yx, and sigma yx is nothing but sigma xy. So this is also same term. So these remaining two terms are transferred to the right side in order to be have a equation dou 2 sigma yx dou x dou y is equal to minus dou 2 sigma yy dou y2 minus dou y capital dou, okay, dou capital Y upon dou small y. Is it okay? So here equation number 16 and 17 you can understand here. That is only rearrangement of equation 14 and 15. Is it okay? So equation 12 and 13 are differential equation. Equation 14 and 15 are the differentiation of equation 12 and 13. And equation 16 and 17 is only rearrangement of equation 14 and 15. Is it okay? Now we are going to add these two equations. These two equations we have to add. In order to get their summation, let us refer next slide. Here these two equations are added. These two equations 16 and equation 17. And that is added here. Is it okay? So after adding these two equations, we will get 2 times of this term here. You can see here that 2 times of dou sigma, 2 times of dou 2 sigma xy dou x dou y, because left hand side same term is there, so that is 2 times. And then this particular equation is referred to be minus dou 2 sigma xx dou x2 minus this particular term of dou x dou capital X dou small x, so that is minus dou capital X dou small x. Then here minus dou 2 sigma yy dou y2 minus dou capital Y dou y. Is it okay? So here addition has been carried. So these total terms are considered to be added here, and that are taken here. Is it okay? So that is the addition here. Then this equation we are going to substitute, because this term, if we take, look to the left side, so left hand side is 2 times of dou 2 sigma xy dou x dou y. And here also, if we refer the equation number 11, then that equation number 11 is also 2 times of dou 2 sigma xy dou x dou y. So here now these terms we are going to substitute. So this particular equation which we got here, so this equation we are substituting here. So equation, substituting equation 11 in equation 18. So this equation 18 in equation 11, that is substituted. And after substituting this equation, whatever the finding we are getting here, you can do this, you can do the practice as a homework at your home, and you will come to know that after solving this equation and uh, similar terms which are present here, if we aggregate the similar terms here, this is the dou to sigma x x dou x, here dou to sigma y y upon dou y2, likewise here. So if we try to bring together the similar terms, and if we take the common sigma yy from first term and sigma xx from second term, then we will get this differential operator as a bracketed quantity. Dou 2 upon dou x2 plus dou 2 upon dou y2, that is the Laplace operator dou that we know. Okay, so this is Laplace operator that we know. So here this will be, if we take the common dou 2 dou x2 plus dou 2 dou y2, if this term dou 2 dou x2 plus dou 2 dou y2, this term if we take as a common, then in bracketed quantity this becomes sigma xx plus sigma yy. Is it okay? And then this particular bracketed quantity will become as del operator. So that is the del square. Is it okay? So del square and this particular bracketed quantity. Then here we proved the del square sigma xx plus del square into bracket sigma xx plus sigma yy is equal to 0. So this bracketed quantity, if we consider here, if we we have derived this thing, then that is nothing but the concept of Airy stress function, because Airy stress function also defines the same term. Del square sigma xx plus sigma yy is equal to 0. So this bracket and this del square term that we can understand here. Is it okay? So with this, now we are considering that sigma xx is equal to dou 2 phi by dou y2, and sigma yy is nothing but dou 2 phi by dou x2. Is it okay? So here these two terms, that is nothing but the stress along x-axis and this particular stress along y-axis. So here this concept of Airy stress function and this concept of this potential function and del operator, if we try to take into the consideration, then one more term we have to consider here, that del raised to 4 phi is equal to 0. If del square this sigma xx plus sigma yy is equal to 0, and if suppose we are considering sigma xx as a dou 2 phi by dou y2 and dou sigma yy as dou 2 phi by dou x2, then the potential function sigma phi is taken outside, and then here we have considered that del square 4 phi is equal to 0. Is it this? Where del square, del raised to 4, now this del square outside the bracket, and once again this bracketed quantity as a del square. So del square into del square, that becomes del raised to 4. Is it okay? And then phi is as it is. So del raised to 4 phi is equal to 0. So that we can understand here. Now let us see that this del raised to 4, that is nothing but a del square and del square. So first del square is dou 2 dou x2 plus dou 2 dou y2, and another del square is dou 2 dou x2 plus dou 2 dou y2. Is it okay? So these two bracketed quantity into phi, so that is equal to 0. So that is del raised to 4 phi is equal to 0. So that we can understand here, and by considering this, by elaborating that concept, finally del raised to 4 phi is nothing but del raised to 4 phi dou x4 plus 2 times of del raised to 4 pi dou x dou x2 dou y2. So here also you made some small correction, that is dou x2 and dou y2, and here del raised to 4 pi dou y4 is equal to 0. Is it okay? So here this particular concept of Airy stress function and the del operator that we have understood now. So with this derivation, now you can understand the concept of Airy stress function, and this particular is function is valid only in Cartesian coordinate system only, with the assumptions of analysis of mechanical element. Is it okay? So maybe now we are going to study the concept of polar coordinate system later on. But for Cartesian coordinate system, this particular equation we are using del raised to 4 phi is equal to 0, first thing, and second one is that is only valid with the given assumptions only. If we are not true with that assumption, then definitely that will be not valid for suppose material is not continuous, then this will not be okay. If material is not isotropic, this equation will not be useful for in that case. If suppose material is not homogeneous, this equation will not be useful. So material should be isotropic, continuous, homogeneous, it should obey Hooke's law, then deformation should be very small. So like this, with these concepts, this Airy stress function is valid. Is it okay? Any doubt regarding this? Anybody any doubt with this particular equation, Airy stress function? Anybody any doubt? Kai Shanka? Okay, Abhishek Godse is saying that no, sir, there is no doubt. Okay. Anybody other?
No, sir.
Okay, very good. Bhushan, Bhushan, Manoj, any doubt?
Yes, sir.
Any
Yes,
doubt?
sir.
No doubt.
No. Okay. Very good. So with this, the concept of Airy stress function is you have understood now. Let us take various small example in order to solve this particular Airy stress function is very we can say it is useful for the Cartesian coordinate system because only we are going to differentiate that particular equation with respect to x two times and differentiation with respect to y two times. So that's why we will start with very small and short examples, and then we will use these particular concepts for actual applications for the large examples that we are going to study for the next lecture. But because, first of all, let us apply this particular concept for small equations. Let us have these three equations, which are small equations. Let us consider the first equation phi is equal to a. Small potential function. A is the function. Now we are considering a, always a is considered to be constant. A, B, these terms we are using as a constant. And ax, y that we are using as a variable. So first of all, the question is prove that following functions are Airy stress function and they represent zero stress condition. Is it okay? So this is the question, and always that is true for the elastic body. Is it okay? So first is phi is equal to a, second one is phi is equal to ax, and third one phi is equal to ax plus by. Is it okay? Where a and b represents the constants. So with usual notations and with usual that definition which we have carried for this Airy stress function, now let us first of all consider phi is equal to a. Then dou phi by dou x is definitely equal to 0 because a is constant, and that's why differentiation of a with respect to x, that is going to become 0. Definitely its second differentiation is also 0, and dou 2 phi by dou x2, that is nothing but sigma yy. Already we have defined dou 2 phi by dou x2 is nothing but sigma yy. So that represents that the stress along y direction is equal to 0 when potential function is constant function. Is it okay? At the same time, if for this function a, if phi is equal to a, then initially let us differentiate with respect to y. This will become dou phi by dou y. This definitely this is equal to 0. In second differentiation, that is dou 2 phi by dou y2, again that will become definitely equal to 0. Similarly, minus dou 2 phi by dou x dou y will be also equal to 0. What this represents? So this represents that this particular equation is nothing but stress along y-axis. This equation is nothing but stress along x-axis, and this equation is nothing but shear strain sigma xy. Is it okay? So this is sigma yy, this is sigma xx, and this is sigma xy. Is it okay? So that represents that stress along y-axis is 0, stress along x-axis is 0, and stress along or shear stress that is also equal to 0. So that's why here it is proved that this particular function sigma is equal to a has 0 stress condition in the elastic body, because elastic body means we are using as Airy stress function. Is it okay? So that is phi is equal to A. Again, a simple equation, if phi is equal to Ax, then phi is equal to Ax. If we use this function, and then let us have that first of all, let differentiate with respect to x. So dou phi by dou x, differentiating this equation with respect to x, what we will get? Phi is equal to Ax is the function. So differentiating with respect to x, that becomes dou phi by dou x. So that will become equal to A. And again in second differentiation, that is dou 2 phi by dou x2. In that second differentiation, that will become equal to 0. 0 again. Similarly, this function phi is here. Initially, if we differentiate with respect to y, dou phi by dou y is definitely is going to become equal to 0. Dou phi by dou y is equal to 0. That's why dou 2 phi by dou y2 is equal to 0 again. Is it okay? So dou 2 phi by dou x2 is equal to 0. Dou 2 phi by dou y2 is also equal to 0. Definitely, if this particular equation dou phi by dou x, if we take differentiation with respect to x, this will become dou 2 phi by dou x dou y, and differentiation of this a with respect to y is going to become 0. So that's why dou 2 phi by dou y2 is equal to 0. That is sigma xx is equal to 0. Dou 2 phi by dou x2 is equal to 0. That is sigma yy is equal to 0. And minus dou 2 phi dou x dou y, that means sigma xy is equal to 0. So for the second case also, that thing has been proved. Now if we refer this equation number 3, then phi is equal to capital Ax plus by. Now let us differentiate with respect to x here. Then it will be dou phi by dou x. Then if we are differentiating with respect to x, this term is going to become equal to 0, and with reference to x differentiation, this will become equal to A. Is it okay? So dou phi by dou x will become equal to A. Then dou 2 phi by dou y2 means this particular equation is sorry, before that let us differentiate same equation with respect to x. So dou phi by dou x is equal to A. So this equation we differentiate with respect to x once again. So that and then we will get dou 2 phi by dou x2 is equal to 0. Now similarly here, if we take dou 2 phi by dou y2, so this particular equation dou phi by dou y, differentiate with respect to y, this particular term will become 0, and this will become only b. Again in different second differentiation, this will become dou 2 phi by dou y2 is equal to 0 here. Is it okay? So dou 2 phi by dou y2 is equal to 0. Then next, if we are going to differentiate this dou phi by dou x with respect to y, this will become dou 2 phi by dou x dou y, and that is also going to become 0 because a is constant term. So which represents that this particular dou 2 phi by dou y2 is nothing but sigma xx is equal to 0. This term is sigma xx is equal to 0. This term is sigma yy is equal to 0, and this term sigma xy is equal to 0. Is it okay? So this is very simple type of example. If potential function is a, if potential function is ax, if potential function is ax plus by, then what will be sigma xx, sigma yy, and sigma xy. And by that way, we have proved here that stress, this particular condition has zero stress condition when this is elastic body, because as body is elastic body, then only we will able to apply the Airy stress function. Is it okay? Now recently we have gone with this concept of biharmonic condition. Is it okay? So we proved this concept of biharmonic condition. What is the concept of biharmonic condition? That is del raised to 4 phi is equal to 0. So what is del? Del is Laplace operator. Phi is potential function. So del raised to phi is equal to 0. That is the condition, and if we take del raised to phi, then this becomes del raised to 4 pi. So del raised to 4 pi is equal to 0 is the biharmonic condition. Is it okay? Now let us have this particular equation for this next equation for Airy stress function. Airy stress function म्हणून पुढचं जे एक्झाम्पल आहे ते एक्झाम्पल आता आपल्याला बघायचं आहे. This is also a small example. हे सुद्धा छोटी छोटीच एक्झाम्पल आहे. This will also be covered in 5 minutes only. Let us take first example now. What is this stress sigma xx, sigma yy, and sigma xy for this equation number 1? So for this example number 1, phi is ax square plus by square. Let us take this first example. Phi is equal to ax square plus by square. Then differentiate with respect to x first of all. So differentiating with respect to x, we will get 2ax, and later on term this will become equal to 0. So 2ax, this is the term which we got here. Then once again differentiating with respect to x, dou 2 phi by dou x2 is equal to 2a. Is it okay? So sigma yy is equal to dou 2 phi by dou x2, which is equal to 2a. That represents that strain along y-axis is 2a. Then let us differentiate this particular equation with respect to y. We will get dou phi by dou y, differentiating this phi with respect to y. So this term will become equal to 0 because with reference to y, x is constant term. We are taking partial differential equations. So x square will be regarded as a constant. That will become a differentiation of constant will become 0. And then by square, for that purpose it will become 2by. Is it okay? So this term of 2 by square, that will become equal to 2by as a dou phi by dou y. Then once again, if we differentiate this dou phi by dou y, then this will become dou 2 phi by dou y2, and this is nothing but 2b, because after differentiating with respect to y, this will become 2b only. So stress along y-axis is 2a and stress along x-axis is 2b. Is it okay? Similarly, now if we take any one of that, if we differentiate this particular dou phi by dou x with respect to y, this term will be constant, which will be regarded as a constant with reference to y. So that's why dou 2 phi by dou x dou y will become equal to 0. Is it okay? So this term we can understand here. So what it represents, so if we write all the results cumulatively, then stress along y-axis is 2a, stress along x-axis is 2b, and shear stress is equal to 0. So this is considered to be a stress values. And then biharmonic condition, for that purpose, if we take del square into del square phi, then it will become 0. So del raised to 4 phi is equal to 0. So del raised to 4 pi 0 means this follows the condition of Airy stress function, because unless and until this condition has been not followed, biharmonic condition has been not followed, this equation we will not consider as a Airy stress function. Is it okay? So that's why this is essential condition, that del raised to 4 pi should become equal to 0. Unless and until this equation del raised to 4 pi equal to 0 is not valid, this particular equation can't be solved by Airy stress function. This is the essential condition. Is it okay? So with this, today we will stop. Anybody, any doubt with this?
Sir, सर्व notes share करा ना group वर.
Okay.
म्हणजे पूर्ण सिलेबसच, म्हणजे आपलं म्हणजे जे काही आहे तुमच्याकडे नोट्स तुमच्या बनवलेले.